All right, this mini lecture is going to be a practice problem. It's going to pull in some old information, but primarily focuses on using what we've learned about standing waves to solve some information. So it reads, a guitar string has a linear density of 8.3 times 10 to the negative 4 kilograms per meter. The length of the string is 0.66 meters. We've tweaked the head of the guitar, those little keys, to a tension of 52.0 newtons. And if I get that string to oscillate in its second harmonic, what is the frequency of that second harmonic? All right, so we are going to want to think about a couple of things. First, we know that the second harmonic of a wave on a string, let's just remind ourselves what that looks like. So that's our second harmonic of a wave on a string. We know in the second harmonic, the wavelength equals the length, the distance between those two fixed points, and the frequency is equal to the speed over the length for this particular example. All right, it tells us that this guitar string has a linear density of, what did it say, 8.3 times 10 to the minus 4th kilograms per meter. And we know that the length between those two fixed points is 0.66 meters. And that string is being held under a tension of 52 newtons. Okay. Well, we're interested in what's the frequency of this second harmonic, which we know to be the speed over the length. And here's where that old information comes in. So how do we get wave speed for a object fixed, or a string, fixed between 2 points? Well, wave speed is dependent on the medium, and that medium is the string. And for a string, the speed of the wave is equal to the square root of the tension over the linear density. So go back and look at that wave speed video to kind of remind yourself of that equation. So now we can just simply apply these principles directly to our problem. So we have the square root of 52 newtons divided by my linear density, 8.3 times 10 to the minus 4. And we find that that wave is moving with a speed of 250 meters per second. So we can use that information into our frequency equation. So we have 250, the length of 0.66 meters, and our frequency of the second harmonic then is 379 hertz. All right, so practicing using these relationships that we've generated by looking at the properties of those standing waves, remembering that it's the medium that dictates the speed through which a wave travels, and applying those principles to solve our problem. Good job.